All right, I'm just punching in a few little other details. I know it got stuck last time, so I don't want to go through in its depth as I did. Otherwise, it's kind of pointless. But I want to say here that slide 39 or something is where we're going to start to see stuff that's actually would be on an exam. Up until that point, it was just pointing out things you've seen in sort of the real world in a normal life, and how chemistry looks to get you to think about these things on the atomic level. So like it introduced carbon monoxide versus dioxide, atoms and molecules. You know, the scientific method is really for lab. You know, solids, liquids, gases. Talked about a few solids, a few things you've seen, charcoal and diamond, and it really foreshadowed for future chapters, like here on gases, and also thermodynamics, you know, how a car engine works. A little flow chart, elements versus compounds, then giving an example between the two, like helium that's in balloons versus water. Mixtures, heterogeneous versus homogeneous, which we'll see all these in greater detail, how you separate these different things. But again, we won't be doing this. If you take, even in Chem 161 labs, you don't usually do many of these techniques, but just pointing out and showing pictures of how you do separate things. And I assume everyone's made pasta and seen a spaghetti strainer before. So this was all pretty much intro stuff. Boiling water and how the math that we'll do behind it in later chapters. Physical versus chemical properties, and showing a few. Again, you can see how there's a lot of foreshadowing for future chapters. Propane, I assume everybody's either used or seen a barbecue and seen the flame on it. The relation of energy, again, foreshadowing for future chapters. And the example I like is, everyone's ridden a bike or walked up and downhill, kind of the same thing. And a car is a big tie-in for these things, right? Gasoline, those molecules are higher in energy. Things that are higher in energy are unstable, and chemicals, especially things that are low in energy, are then more stable. So everything that comes out the tailpipe of a car doesn't have much energy. It's lower in energy. The energies in the bonds of the reactants. In this case, the gasoline. Okay, so then to 39, and this is, usually I think the first exam in Chem 161 is really easy. It's sort of a review and a buildup of all the basic science classes you've had your whole life. It isn't really till after the first couple of chapters. Chapter 4, I think we'll really dive into hardcore chemistry, and that's, reactants and products and grams versus moles. This is sort of, let's make sure we're all on the same unit. And some of these things, again, why it's sort of a review of all the science you've covered, is that we're not going to do much, for example, here with meters, a little bit when we cover light, because that's how the atomic model works. Some of the things we do with the speed of light, frequency, and whatnot. But most everything we're going to do is with grams, right? And temperature too always has to be in Kelvin, because it starts at 0, right? The Celsius and Fahrenheit scale have negative numbers, and we'll see in the beginning here where we're just talking about things, it's not too big a deal. But as you move on, and especially in Chem 162 as well, if you put in negative numbers, there's no way to get the correct answer for whatever you're solving for in the equation. All right, then just a few definitions, right? These different units, say inches versus centimeters, miles and kilometers is another example. So there'll be a few, one or two of these type of problems, especially when we get to the dimensional analysis. And some image, my computer's maybe getting too old. More conversions. And if you go through, you'll see some of these problems and examples in the book and whatnot. We're going to stick in grams, and at times you'll see problems where there's changing from kilograms to grams, but that'll only be on our first exam. After that, it's just moving a decimal point 3 places, and we have more important things to cover. Time we'll only see when we talk again about the atomic model of the atom, and that's because the speed of light is always described in meters per second. But beyond that, it's a chemistry class. We're not doing, when a train leaves Detroit headed for Cleveland at 60 miles an hour, etc. That's a physics class, so we won't use the unit of time that much. Temperature, again, we'll do everything in Kelvin. Now, when we're talking about things, we might use the typical Celsius scale. I know that we use Fahrenheit in the States, but you'll want to become more familiar with Celsius. And some of the obvious ones, temperatures are related to water. So freezing is 0, boiling is 100, and then room temp is in this like 22 to 25 range, and your body temperature is 37. So anything over 37 then is considered pretty hot to us. And we talked about this a little bit, right? Heat flows from matter that is higher in thermal energy into lower. So, obviously when you take a tray of cookies out of the oven, you burn your hand if you use a pot holder so you don't burn your hand, right? The tray of cookies, the metal of the tray pan is hotter, and it transfers that higher energy to your hand. Same thing when you hold an ice cube out of the freezer, your hand is transferring its energy to the ice cube. Right, hotter things transfer their energy to cooler things. So it's all relative. Okay, then we're working up to our first equation, and really what I think is more important or unique, better, higher brow about college than things when you're younger is that they show you where the equations come from. So between Celsius and Kelvin, you just add 273 to the value, right? That's pretty easy. But you need a different equation getting to and from Fahrenheit and Celsius, and it's because the units aren't the same size. And where the formula comes from is here, right? From 0 to 100, there's 100 units. They happen to be in Celsius. From 32 to 212 is 180 units of Fahrenheit. And so they're not the same. Degrees in Fahrenheit and degrees in Celsius are not the same size to one another, just like miles and kilometers are not the same size. So there's an equation that relates the two. And so the way you get there is you subtract 32, right? Because they're 32 degrees off, right? The 0 scale for Fahrenheit isn't lining up the same as the 0 scale for Celsius. So you account by that by adding on the the 32. That moves the Fahrenheit scale down to equal to the Celsius so that they're both at 0. And then the 1.8 is just the 180 units versus the 100, right? If you divide both of those by 100, you get 1.8. So we'll do this off and on throughout the, all of college, where they should be in your different science classes, where they explain where these equations come from, then it's not black magic or something. Now this one's kind of the simplest of equations. All right, then Kelvin to Celsius is just 273. Not much to say there. All right, so there'll be one of these on the first test, converting one unit all the way to another unit, whatever it is. And you can't go from Fahrenheit to Kelvin directly. You have to go through Celsius. So most likely what's going to be on the exam is either from Fahrenheit to Kelvin or from Kelvin to Celsius. Anyway, this one works through 40 degrees Celsius. right? To get to Kelvin, you add 273, pretty straightforward. And then the bottom one's slightly more challenging, but this is where we use the new equation, right? So in this one, you just need to make sure you plug in the right amount, the value in the right location, which is critical for later equations. You want to make sure you keep track of units. And then what's nice about a lot of these problems is when you can rationalize, does the answer make sense? So if you know that your body temperature is 37, and you can see that 40 is above 37, you know your body temperature is 98 degrees. That means we're looking for a temperature that's above 98 degrees Fahrenheit, but not terribly high, right? It's kind of close, 37 versus 40. So this answer of 104 seems reasonable. Okay, when it introduces these prefixes, there's obviously a lot of them. And this idea of power of 10 is the way scientists talk about things. So as we do things, numbers can get really big and really large. And how close numbers are is by this power of 10, or what's often called an order of magnitude. So if you hear me say an order of magnitude, if I say something's only 2 orders of magnitude off, what I mean by that is it's 10 squared or 100. Okay. If it was an in-person class, I would say you need to memorize a few of these, but since it's an online class, which makes the exams basically open note, open book, you could have this taped up on the wall during your exam. And we won't use too many of these things anyway. Milli we will use because in your labs and whatnot, that's a reasonable size to weigh out things on a scale. So in these chemistry labs, 100 years ago, they used large amounts, and it's just wasteful if you're doing an experiment that you already know the outcome as a teaching lab experiment. So to put 500 grams or a kilogram or something of material just to put it in waste or wash it down the drain is a waste. So nowadays they use much smaller amounts to conserve. And then the rest of these kind of depend on what field you're going into. So like mega is this huge number. So imagine if you're in an engineering class and you're talking about the pressure on a column of concrete that holds up a freeway overpass as 3 dump trucks drive over the top of it. That pressure is going to, you're going to need a prefix that gives you a huge value. Kilo, it'll be introduced here in, like, again, a physics class, how many kilometers or something, but we're not going to use that too much. We'll use milli and occasionally micro, but not very often. And then only nano when we talk about light. We'll never use pico. So chemistry kind of tends to stay in this kilo to milli range. And then if you're in biology or if you're a bio major and have looked at classes, you might have noticed already microbio is a course you have to take. And you look at something through a microscope, it's small, right? And so this micro makes sense. I'm not going to test you on these individually, especially in a class like this where you could just have it taped up on the wall. So that's a little, testing you on some of these things in an online open book, open note class is a little too easy and a little silly. Okay, for volume, this is the take-home one down here at the bottom in red to memorize or know, because we're going to do a little bit of density work, and a milliliter is the same as a centimeter cubed. And it's not much of anything to memorize or know, since it's a value of 1 and 1. It just means when you see, when we flip-flop back and forth between solids and liquids and look at their densities, you can interchangeably go between centimeters and milliliters because it's just 1 versus 1. Okay, again, it's not a physics class. There's not going to be a problem that asks you, a train going 40 miles an hour from Cleveland heads towards Detroit, and it's going, 85 miles an hour or something. What time did it meet? So these are these conversion factors if you need them to do some of these problems. And when we get to dimensional analysis, this is a good example of making dimensional analysis more tangible and relatable. But there might be like one problem like this on the first exam, but you'll never see it again on the second or the third or the final. Okay, I don't see the reason to memorize any of these mass ones unless you plan to work at the post office or deal illegal drugs or something. It doesn't really seem relevant. We're just going to stick with grams. And when you order things from chemical companies and you work in a chemistry lab, everything has grams written on it or kilograms. They don't have pounds and ounces. Maybe a chef if you're going to go be a chef for some reason. Liters, again, your labs that you're going to take, they're really trying to minimize the amount of waste. And so you're rarely ever going to use over a liter of anything. And it's just going to be milliliters. And here you can see that same conversion, milliliters and centimeters cubed. Okay, density. So what makes up density is the mass and the volume. And these are extensive properties. So the value depends on how much material you have. But density is an intensive property. It doesn't matter how much of that material you have. And by that, I mean, you know, an aircraft carrier is made of iron, and so are nails. And it doesn't matter whether you have a tiny little nail or you're talking about a huge aircraft carrier, the density of that iron is the same. Right, and so you can graphically show this by taking the mass and the volume of you know, they picked brass here, different sizes of it, and you get obviously then different volumes. They go up as the size of the object goes up, but the density stays the same. And this is your classic X and Y. This is our first example of a straight line plot, right? Y equals mx plus b. But here the plus b, the intercept is 0, right? If there's no mass, there should be no volume. That means you don't have any more of the item, whatever it is. And so the slope of the line then is your density. And metals are going to be higher, non-metals are going to be lower, right? You've seen things that float on water is one, things that float have a lower density and sit on the surface, and things that are heavy, like a penny, when you flick it into a well, a fountain, they sink to the bottom. All right, so mass over volume. Again, there's different units to use for this, right? Centimeters and milliliters are interchangeable, so that's really the same thing. And then make note, gases, right? You've been in the water, you blow a bubble, it goes flying up to the surface. The gas is much less dense, and it's described so that its number is more reasonable in grams per liter, so a much bigger volume than solids and liquids are described as grams per milliliter, again, or centimeter cubed, but those values are the same. All right, then this just shows, this table here on the sides, kind of good, shows some relative amounts of things. Let me make this a little bigger and get rid of that. Sorry, like you move one thing in Zoom and it just moves a bunch of other things. Oops. There, a little better. Okay, so ice will cover Y, and we'll see water, we'll use it off and on throughout the semester and in 162, and you've seen that ice floats. It's a little less dense, but it's pretty close. That's where that's saying the tip of the iceberg. If you put sugar in your coffee, it sinks to the bottom, right? It's a non-metal, so it's not that dense, but it's a little more dense than water, 1.58 it looks like. Salt, the same thing. Not that you, I imagine, put salt in too many liquids you drink. Then the rest of these things are metals, and you can see they get heavier and heavier. They picked heavier examples. And this is one of the ways they figured out, made sure people weren't cheating you if you were buying a gold necklace a long time ago, is that gold is very dense. Platinum's a really expensive metal too, but you couldn't just take lead and paint a little gold over it and pass it off as a piece of gold because the density would show. It's a little frozen. There we go. So there'll be some density problem on the first test. Again, we'll see density off and on, but I'm not going to put it back on the final. These first exam is usually pretty easy. Again, a sort of a general science review, not really chemistry till chapter 4. And so there's only 3 things in the equation, right? The density, the mass, or the volume. So you're going to be given 2 and asked to find the third. So simple algebra. Just make sure you rearrange to solve for the unknown thing, whatever was missing from the equation. In this one, they gave you the grams and the centimeters. Not surprising whenever they introduce a concept like density. Here, they make you solve for the density in the first problem. But as we'll see, real typical in science and chemistry, especially when they introduce some concept, once they have you here solve for density, the next problem, they give you the density in either mass or volume and have you solve for the missing thing. Okay, so some of this stuff, again, is really more for your lab, right? I don't know if your labs are in person or online and what the instructor has planned for them, so they might cover some of this stuff over again, so we won't spend a lot of time on it. Water forms this meniscus like this, and it's because of surface tension and hydrogen bonding, which we'll get to way later in the semester, but you measure it off the bottom of the meniscus. So this, you got to have a unit. There's no point in a value without a unit. It's like if someone asks you how old you are and you said 3072 or something, and they look at you like you were crazy because maybe they assumed you mean years, but what if you mean weeks or something, right? So a number isn't any good without a unit, and a unit isn't any good without the number. Scientific figures are not going to be too critical for us because it's not a lab, we're not measuring things, but usually what you do is you take estimate the last digit that's missing off the device. And this is very, for things you're doing with your eye versus a lot of things nowadays are digital and it tells you what the item is, so even this, like these aren't the scales that you'll be using in lab where it lines up and you're estimating the last marking there. So, and I'm certainly not going to put, this picture on the test and ask you what the weight is. All right, sig figs. I'm not real strict, real big on sig figs. I'm going to try to trick you with them. And I'm not even going to put one on the first problem or the first midterm. So we'll just go over this briefly, right? All non-zero ones are significant. Interior ones clearly are significant because you've somehow measured the number before and afterwards. So it's only these ones that, like for example here, this one's just holding the place, right? It's only the 1, 0, 5, and 0. If this was some instrument, it would have measured the 0. But these leading zeros, they're just telling you the place, the size of the measurement. Now trailing zeros, it depends on whether it was measured or like here, for example, it's not really clear whether the instrument maybe measured the 1, 5, and the 0, or just the 1 and the 5. So when you put it into significant scientific notation, then that'll be implied. Now for us, it's not really going to matter too much. And let me go back to the density problem and just show you why. So for example here, right, this is giving you 3 sig figs of the 2.33 and up here 3.15. So they're both 3 sig figs. So your answer needs to have 3 significant figures. And that's how all of our problems are going to be. I'm not going to mark anybody off on a problem where they've used an equation and know all the units and the concepts going on because they put an extra sig fig on there. You won't get a 0 on the end of it where you have to decide whether that's significant or not. It'll be like this, where all the numbers given in a problem have the same number of significant figures. So here just walks you through a couple of those same examples. That 0 on the end there is, it's saying that it measured it. Here they're all sandwiched between. This one's an exact, right? D is deci, so by definition, deci means 1/10 of the other thing. So here the sig fig is put there on purpose in scientific notation. So then it's leading, and then this one's ambiguous. But again, it won't be ambiguous on the problems that we're doing. Okay, so these rules for it, when you're multiplying, you keep the smallest number of significant figures. And then so here's and dividing as well. So when you multiply, this is on almost everything we do, you're going to multiply or divide somewhere in the problem. So whether you're multiplying or dividing, you keep the number of sig figs the least that's in the problem given. So that's why typically in these problems, I give you where the numbers you're going to be doing algebra with have the same number of sig figs, so that it's not really an issue. When you're adding and subtracting, it goes by the decimal place, right? So for example, this 574 saying, it measured it to the hundredths place. And then over here, it's saying somehow it had a measurement to the thousandths. And there's no reason to report the thousandths because you're using an instrument that wasn't certain of the thousandths. So there's no reason to think that the answer, the 4 here in the answer, is certain either. So adding and subtracting, you do the decimal point, the last, whatever the placing is. But again, almost everything we do is going to be multiplying and dividing. There's not that much addition. Okay, then roundings, we don't need to spend a lot of time on this. 0 to 4 is down, 5 to 9 is up. I'm not even going to go through those. I think everybody's seen and done that their whole lives. Here's just a couple examples. Again, we're going to be multiplying things, and that's what's most important. I'm going to give you numbers like you saw in the density where all 3 are the same. So I'm not going to walk us through all these. Precision and accuracy. Again, this is a kind of more for your lab class than for us to spend too much time on. And I think the pictures show it a little better here. So here's some data where they're saying like student A, B, and C, and they're trying to measure something, whatever it is. And clearly it's supposed to be like close to 10. Right, the first one, the values are above and below the mark where they should be. So it's kind of inaccurate and it's not very precise. The next one, all the data, and you can think about this like if you made a machine that was shooting darts at a dartboard. The blue would be the bullseye, let's say. Here in the next one, all your darts are hitting the dartboard really closely together. So your dart throwing machine or gun or whatever, it's fairly precise. It's just not calibrated, so it's inaccurate. It's off. Then of the 3 here, this student, his dart throwing machine is really close to the bullseye, and a little variation above and below it. So it's both accurate and precise. Again, this won't be on the test. It's more of a lab class. And then here's the actual darts. Before it was numerically shown. Here's sort of the dartboard. Right here, it's all over the place with big variation. Then B, it's precise there. It's tight, but it's not accurate. It's off. And then C is where it's both. Okay, this part, dimensional analysis, which is just converting units, is good to work out some of these problems and make sure you're comfortable with it because you're going to do it all year long in Chem 162 as well. And if you're a science major in all kinds of science classes. So a conversion factor is something where you have one thing is equal to another. And there's 2 ways to orient it. Now, which way it goes depends on you and what problem you're tackling. So whatever unit you're given in the problem, you want that unit on the bottom, right? Because they'll cancel each other. Then you're going to move along into some other unit the desired unit. So this one is real simple here, where if I said how many hours in a day, right? Well, there's 24 hours in a day, so that's the unit you want on the bottom. Then hours on the top, you'll get the answer in hours out. These seem kind of sort of silly and easy in the beginning, but they become more important, especially starting chapter 4, where we're going to start using units that people usually aren't familiar with, grams and moles and things of this nature. So here's a little strategy. I'm not going to read it to you word for word. You should tackle some of these, and then if you have some problems, come back and go through, and if this is useful. But I'm assuming everyone's done this at some point, so this is just sort of a refresher. Okay, and here's a good example, because there's nothing to take you from yards to centimeters directly. You've got to go through some intermediate unit. They chose meters here, which is totally reasonable, probably the best one, right? So the thing they gave us was yards. That means our first conversion needs to be in yards and get us which gets us out of yards and into another unit, which can then move us towards the unit we want, centimeters. So here, yards gets us to meters, and then we're out of meters and we're to centimeters. And so for this one, the number you were given had 3 sig figs, right? 1.76. So your answer should have 3 sig figs. So just round the 8 up to 1, and the answer is 161. This one, milliliter to quarts. Again, we have 3 sig figs, so that's what we're going to want in our answer. We need to get out of milliliters into something else. We have this conversion factor of liters to quarts, so we want to get into liters, have the liters cancel, and we'll get to quarts. Now, I know some of these, especially the time ones or distance, you're so familiar with the units, seconds to minutes, minutes to hours, hours to days. But as we move along, we're going to do grams to moles and moles to moles. And they're units you haven't dealt with or are familiar with. Slide 91 is just relating these, like the cubic, the centimeter cube. So when you go to volume, right, to get that cube means you multiplied it 3 times. And so if you wanted to switch between centimeters and inches, which is 2.4 to 1, you need to cube that as well, right? And so 2.54 cubed is 16.4. That's where this came from. I don't know that we'll even do this. You might see one, in the book. I'm not going to put, one of these volume ones on the first exam. So we're not doing, we use a little bit of density in the beginning, and we'll see it again, but we're not usually converting the density between separate units of inches and centimeters. Here's another one. So you can see 5.70, that's 3 sig figs. Your answer should have 3 sig figs. They gave us liters, and obviously this is a volume one, but we won't be doing this, the rest of the semester. Liters to milliliters, milliliters to centimeters, and then centimeters to inches. So, right, the unit they gave us, we want to get out of that. Right, we're in another unit that's still not the one we want, so we need to get out of that. So that second milliliters on the bottom. Centimeters cubed, we're getting closer. And to get out of the cube, we need the units to match. So we need centimeter cubed on the bottom and inches cubed on the top. And that's what they want. And then round. Here's another one. But I think, we've done enough of these. 3 units, so your answer, round off 3 units, and have your, units you're in, units on the bottom cancel, and move along until you get the units you want. Density is a conversion factor, right? So when you're given density, it has some sort of mass over the volume, and you can rearrange that and flip it, right? So the density of water is 1, and 1 inverted is still 1, so it doesn't change much. But let's say, like for example, here it's doing lead, and that's 13.1. To rearrange that, it's really 13.1 is equal to 1 centimeters cubed, but remember that's the same as milliliters. So then it just depends on what units they gave you. So what's showing here is that it gave you 4 centimeters cubed at first, so you need that centimeters cubed on the bottom. But it could have done it the other way, where it gave you the lead and you would need 11.3 grams of the lead on the bottom. Whoops. And so they do a problem here. What's the mass in kilograms of 173,231 liters of jet fuel? That's a lot of jet fuel. So I'm expecting a big number, right? That's a big number. And then it tells us the density. So first thing is our units, right? Here's, and these things are helpful here if you're tackling the problem or you go back through these, especially with the animation, which, you know, I'm not doing the animation because it freezes up this computer apparently, but it shows these step by step. And this is sort of your roadmap to solving these problems, right? It tells you what you're given and reminds you of what you want. Then, you know, this is your map, your plan of how to get there. And the things, the tools that are going to get you there, right? And then it lines it up, and this is dimensional analysis, right? Our liters cancel, then our milliliters cancel, then our grams cancel, and we get to the unit they wanted, kilograms. And it's the density was near 1, and so we're expecting numbers similar in size to what we had, but in kilograms, right? And milliliters to liters and grams to kiloliters are both 1,000 unit conversions. So those, in this instance, don't really make that big a deal. It's really the density that has the effect of changing the value. Okay, so equations, we've seen a couple of them already, and all of these that we'll do all semester, it's not quadratic stuff. It's going to be solved for the unknown. So you'll be given, we'll be using an equation, and you'll just be solving for the one thing that's missing from it. And they're introducing this here with density, right? So there's 3 things in density because we saw in that plot in the y equals mx plus b form, there is no b because it's going through the origin. So in any of these problems, all they're going to do is give you 2 things and ask you to find a third. And as we move along, we'll get to equations that have 4. I don't know if we have any with 5 in them, but in Chem 162, there's a couple that have 5 in them. And you'll always be given everything but 1. And that's the one you're solving for. So again, here's another example. It wants you to find the density, some metal cylinder, and it tells you the mass. And then this one's making you go and hunt a little bit, right? So this is really more like you could have this same problem in an intro physics class as opposed to an intro chemistry class. We haven't really talked about specific elements, which is what chemistry is about. This is just, you know, a density of physical property thing. All right, and the tricky thing here is the volume they're not giving you. They're making you indirectly go find it. So how do you get that? You need the area of the circle, and then the length, that gets you to the volume. So finding the volume, pi, and then the radius squared, and then the length, that gets us to this volume. They're underlining it because if you look up above, we have 2 sig figs, and we're going to multiply and divide things, so our answer should have 2 sig figs, right? And we want mass over volume, and then round it off, right? And 0, obviously, so 4.5. But again, I'm not trying to trick people with, you know, you work through a problem and use the equation correctly and then don't round correctly. So on a test, especially if you show your work or something, and that's why it's worth it to snapshot that and email me your scratch paper. But that only come on our fill in the blank problems, and I haven't decided how many of those we'll have. We mentioned the order of magnitude, which is really just the scientific notation. And the order of magnitude is just that value on the exponent. Things we count by our fingers up to 10 and start over again. It's a 10 basis system that we use. There's other units that you're aware of that don't do that, right? There's 60 minutes in an hour, not 100. There's 24 hours in a day. So there's other units you're used to that start over at different values than 10. but excluding those unique ones, everything we do by 10. I'm also not I'm not going to be like marking off people for not putting things in scientific notation. Sometimes it's just easier to write them. So you should know what it means, but maybe in your lab class they will. But our focus is the equations, the understanding, and the chemicals, not marking people off on things because of sig figs or the scientific notation. And this is a good example though here, right? So we're going from years and seconds, right? 1.2 times 10 to the 5th atoms per second. How many for a year? So this is a good one where it has a lot of units that you need to set up to cancel. So 4 years what they gave us, but the unit up above was per second, so they don't line up. So we got to go from years to days, right? Days to hours, hours to minutes, minutes to seconds, etc., until we get to atoms per second. Kind of a strange example though, but anyway. So that's the last slide. All right. Let me open up to, thought it was already open, but so most of that, again, had the feeling of a generic science class. Right, we didn't talk specifically, a little bit about the densities of different metals in there, but that wasn't really chemistry, right? It was kind of more just generic science, which could be covered at the beginning of, maybe not a bio class, but any sort of physics or engineering or chemistry class. It kind of overlaps and wants to get everything started and have everybody on the same page from the get-go. And it's opening slowly for some reason. There it goes. Where did it pause? Let me try this again. I don't know why I just paused it all of a sudden. Okay. There we go. Okay, so this chapter you can see we're gonna get away from just simple units and sort of a basic, science class and start to dive into things by atoms and elements. And it covers a little bit of historical stuff, which I like, that kind of makes it more tangible and explains where these things come from. And so this is trying to show you one of the ways they, if you're into nanotechnology or electrical engineering and stuff, it's kind of showing you one of the ways that they started to look at the surfaces of microchips and things of this nature, which is difficult to do. And it walks us through a couple of these different techniques. Scanning, tunneling, microscopy, and it gives you the names for them, but it's not a history class. You don't need to know these things. One of the way these things work is you'll have this tip and it goes over the surface and it measures the current as it flows between the surface and the tip. And as that current changes, that tells you information about the density, the distance, and then it translates that into like a topographical map. So if you've ever seen a topographical map, is one of those where, like, let's say at mountain range, it actually bumps up on the page and it's in 3D. And so that's what one of these pictures is trying to show you. All right, and so the way these things work is very grid-like, where you have this tip and it's held above the surface and it just goes back and forth, kind of like a printer printing. When you hit print on a big paper you turn in, and it goes, well, it goes one line at a time and starts over. This would zigzag back and forth, and they've left spaces here exaggerating it. But anyway, it goes across, and that tip measures that distance. And then you can get a feeling for what the surface of this is blown up, not the scale, right, of like a computer chip, something you can barely see under a microscope. And this will tell you different things about the surface. I don't really know what the point of this picture is. Anyway. All right, so a long time ago, these scientists started to come up and believe that there are these tiny, tiny things, and that they were little particles. Here you get some famous names, and these are more Plato and whatnot, theory and whatnot, than they are scientists. And so really the world started to change. There's the scientific revolution and there's the industrial revolution, and the two kind of overlap because you need some of these materials and things to discover these things scientifically. The law of conservation of mass is just that mass isn't created or destroyed, right? It just transfers location. So when you do a chemical reaction, whatever you put in has to equal the weight of whatever you get out. And this is true when your exposure, what you're used to, this would be in the kitchen, right? You mix in a couple eggs, flour, water, sugar, chocolate chips, whatever, and you make chocolate chip cookies. You put it in the oven, and the mass of the cookies coming out is the same as the mass that you put in. The only thing that's missing is the moisture, right? You put it in the oven, and so it's heating up. It's interacting together, and the moisture is being driven off by the heat. But what this means for us is, so here they're saying, if you were going to make table salt, and you don't make table salt this way, it's already in the ocean. So you'll see this, especially in third world countries, where they'll have, either use the tide, or they'll have a place where you can let the water in, and somewhere real flat and shallow, then the tide goes out and they shut the door, and the salt gets left behind. Then you can just collect it. But if you were going to make it, if you took, a chunk of sodium, the metal, and chlorine is actually a gas, but if you react these two together, whatever the mass of the sodium and the chlorine, you're going to get the same total mass as the product, the table salt. Then they started to notice in all these samples, regardless of their source, they all seem to have the same proportions. And right, water is H2O, it's not H3O, it's not HO. And they started to notice these kinds of things. It didn't matter where they got the sample from, it had the same ratio. So it didn't matter where you got some table salt, the ratio of the chlorine to the sodium was always the same. And again, that's because the formula was already the same, which you already know now by things like water, obviously the most common, H2O. And so they started to notice these whole ratios of them. So for example, carbon monoxide and carbon dioxide, they were noticing you get these ratios, right? And they're basically coming up with the molecular formulas. Right, Dalton is a name we'll see quite a bit because a lot of his experiments, he's really a physicist. So it's really physicists that devised and made up these experiments that proved atomic and elemental patterns and whatnot. So he comes up with these ideas, right, that there's these tiny indestructible things, he calls them atoms, and that samples would have the same mass, so the same atom in them, even from different samples. That's those ratios. They're coming up with these whole number ratios. In these chemical reactions, one atom cannot change into another atom, right? So we eat food that is carbon-based, and then you breathe out carbon dioxide. You don't eat food and then breathe out some other gas, right? You need carbon-based food because that's what we metabolize. You're not going to start breathing out some other gas. And one of the reasons, you can starve to death is you have to breathe out carbon dioxide, and you actually lose weight while you sleep. You need a really accurate scale to do this, but if you slept 10, 11, 12 hours, the longer you sleep, the more you notice it. And you're losing weight in your breath. You're breathing out carbon dioxide, so you're always losing carbon. Okay, then you need the Industrial Revolution to set up these experiments that we'll see. But what they started to notice was charges on things and the way charges behave. So if you've ever played with magnets, you've seen this, right? The positive and the negative ends of a magnet attract each other and stick together. When it's the same charge, they repel one another. And then also, if you have equal and opposite charge, they would cancel each other, and the overall charge would be zero. Okay, so how did they arrive at these things? This is where we'll look at some of the instruments that did this. So this first one's a cathode ray tube. And this is why you need the Industrial Revolution, because you need to melt and blow glass. You need electricity. And so what this is it's this glass tube where you have a vacuum and you can evacuate all the air. Then you've got to have a voltage source. And they saw this glowing coming off of it, and that's the electricity passing through, which a lot of these things is basically like a neon tube, right? Neon sign. Another name you'll see a lot, again, not a history class, you don't really need to make note of this unless you're a physics or engineering major and you want to know the history behind all these things. So his concept was that the cathode ray was composed of these tiny charged particles. So he's trying to figure out a way to demonstrate this and what kind of force it takes to deflect the path. The relationship analogy here is like measuring the amount of force it takes to make a car turn. So if you set up this little experiment, this would be a good one to see if the animation, the full screen will work. Hopefully it doesn't freeze. Let me know if it does. We'll see if this works. So, should get that away. Here's the power source, right? A negative and a positive. So there's attraction to it, and the power source is basically just electrons. Then you've got these two plates here. It looks like the animation is not working for some reason. Yeah, it's not working. Anyway, so an electron, if you shoot it through, it'll be electrons are negatively charged, it'll be attracted to the positive of the plates. If you pass light through something, light has no charge to it, and so it won't have any curvature. Yeah, I don't know. And that's what these two were supposed to, animation were supposed to show up. And right? An electron is negatively charged and gets pulled to the positive plate. But light, like a laser pointer, if you shine light through it, it has no particle, no ionic character to it. And so it would pass directly through and hit the other side. And this is basically how something called a mass spec works. If you stay in science, you'll use a mass spec. That's kind of what this is trying to show. So a mass spec tells you the mass of something, and it relates it by the charge. So it'll fly, and then whatever the charge is, you have a couple plates here with some charge, and that deflects them. And then how far it moves off, if it was just, say, purely light, it wouldn't deflect at all. How far it moves away tells you something about the charge and the mass. So if it was +1 versus +2, but also how heavy the ion is. Right, so, and again, it's not a history test. You don't have to, there won't be anything on the test with this. This is just explaining how they arrived at things. So tiny particles, the cathode rays, they notice electrons, they have negative charge. The beam, because the beam always went to the positive plate, and they knew the deflection was by these two factors, charge and mass. And every material they tested all contained these same things. These, we know them as electrons. And they found it to have this ratio. If they used hydrogen gas, this is what they saw. And so they're basically narrowing in on the properties of an electron and an atom, a proton. All right, so then when they do this, by those two values, what they notice is that the hydrogen atom is like 2,000 times more in mass than the electron. Millikan is another physicist that designed experiments and basically showed the same thing. All right, so they're narrowing in on electrons, right? Everything seemed to have these things. That's the building blocks of all matter. This is Millikan's famous experiment. So you've got, again, you need the Industrial Revolution, but you've got a way to view it. You've got a way to like put out some sample into ions and spray it real fine, like a squirt bottle. You can put it on the mist, that kind of thing. Then you can have your light source. Here's your plates. And the idea here is you can get it where something drops through this tiny little pinhole and these tiny little drops. And if they're ionized, the drops, you can watch them drop, and some of them then might float and seem to defy gravity, and it's due to the difference in charge between the plates, and that being the same charge as the drop itself. All right, so from this, they basically figured out the charge of an electron and then the mass of an electron. All right, so it's no longer indivisible, and more names you'll see. Thomson's must propose a new model of that to replace this like atom versus Dalton's, and there'll be new experiments that come up and refine these things. Again, it's not a history test. We'll see the Curies come in here. There were a couple, they're Polish. We'll see this again in nuclear chemistry. Rutherford's also a name that you'll see, and you needed radioactivity for some of these future experiments that they're going to outline. An alpha particle is a hydrogen atom that has positive charge. The beta particle, which you'll see in Chem 162 probably, is basically just an electron, right? There's the 1/2000th of the hydrogen, which is what they were seeing before. And then gamma rays are high-powered rays. So if you've had a broken bone or something, you've gone to the doctor and you've got an X-ray, they put the lead blanket on you. Gamma rays are higher energy than X-rays. So you need, like 6 inches of lead or a foot of concrete to stop X-rays. Whereas to gamma rays, but X-rays, you just need a couple millimeters, and that's where they put that lead blanket on. All right, so they know there's electrons and they're getting the mass of hydrogen, but they're really still not certain on what the atom looks like. So Rutherford's, this famous experiment of his, was trying to figure out the orientation of it. What does it look like? How do you prove something's empty? Well, you can shoot something through it. This is sort of the classic magician where they put their assistant, in a box and they shove knives through it. And then with the nuclear chemistry, the radioactivity they use, they're trying to figure out these subatomic particles and what's going on. Well, you need small things to do that. So it's sort of like a target with a gun. So your bullet is the alpha particle, and then they took just like aluminum foil, but they used gold because it's much bigger and heavier, and basically rolling it into a really thin sheet to where it's almost one atom thick. Now gold has a heavy mass, 197, let's round up and call it 200. And they knew that the hydrogen atom, the alpha particle, was a 4 and had a +2 charge. So this is basically what it looks like. Imagine, you're at a gun range and the gold foil here is your target. This is your gun. The lead here blocks the gamma rays. And then they have, it's an entire box, and you have some radioactive source in here. And then there's a little pinhole, the only place for the alpha particle or the bullet to escape. So it's your pseudo gun, right? And then what they noticed is most of the time it just passed right through and nothing happened. And every now and then it would deflect off, kind of like the way, if you throw a ball, tennis ball or whatever, at a wall, and it glances the wall or hits something and it changes its path. But every now and then they would see that it would come back, right? Come shooting back to them. Now, this is where you need to keep in mind that the gold has a mass of 200, the alpha particle of the bullet has a mass of 4. So if you've played pool before, you hit one ball into the other, right? And it takes the energy and bounces off. So what you're seeing here is that it made some kind of collision and actually bounced back, where most of the time it just passed straight through. So that tells you that most of the volume is empty. And this is another one you can try it at home, the animation. Most of the time it goes through the screen and goes straight through, right? Which means that it's basically the majority of the volume is empty. Then every now and then it deflects off, but once in a while it bounces and comes striking back. And what were the numbers of these? About 98% went straight through, no effect, which means the volume is basically 98% empty. Then 2 deflected off at angles, but it's not a clean hit at 2%, so still the volume is like 99 point something. And then every now and then these alpha particles would actually bounce off. And the analogy here is like if you fired, a 15-inch cannonball at a piece of paper and it came bouncing back and hit you. That would seem strange. And so what they arrived at is that the atom's mostly empty space because everything went straight through. So that means that it's got some dense center, but it had to have a volume that was really small. So large in mass means a real dense center. Big volume, large mass, but only in that one spot. And that explains how these things bounced back. So the 200 mass for gold wasn't evenly spread out. It was condensed. It was held together in this tiny spot. And then the only way things would bounce off each other like this was if they had the same charge. And so the idea here, this was sort of the theory before. And now we're narrowing in on what the atom looks like, right? Is that this thing's big, and it's only the direct hit and the positive charge that makes it come back. Normally it just deflects it off, and most of the time it's going straight through. And on rare occasion, right, the hydrogen's positive, so it comes near this, and the charges repel each other, and it goes shooting and deflecting off. It doesn't actually even collide. And this is what we now know as the nucleus. right? And it's this dense, tiny little center. It's the entire mass. Those electrons that are circling around it have tiny mass, and they take up this large empty volume. The nucleus is positively charged. That explains the deflection back in the exact opposite direction. And they call these things protons, right? So it wouldn't bounce off unless they had the same charge. So they knew that the protons are positively charged and those electrons were negatively charged. So to be neutral, since it had both these things, the only way for it to be neutral is if it had the same number of protons and electrons. Right, then arriving at the mass of these protons and neutrons basically came from carbon, right? So after you've had a barbecue, campfire, what's left in the fire pit is almost essentially just pure carbon. You'll have a log and most of it burns, but what wasn't able to burn was the carbon. And so what they found when they compared it to this, pure source for them, is that it was 1/12 of these masses, and you knew it was same number of protons and electrons, and so there must be 6 protons and 6 neutrons. And these values is where they came up of what's called an AMU, the atomic mass unit. And the electrons were 2,000 times smaller than that, so about 0.00055, which we're never going to use the mass of an electron. It's basically irrelevant. Okay, so as you get beyond hydrogen, you have elements that have more and more protons, but they're positively charged, so they should repel each other. And what's that extra mass? It basically, you can think about it as a proton and electron combined, and that gets you to a neutron, and it buffers that positive charge, right? So the proton and the neutron are both there in the nucleus, combining to give it its mass. And its mass unit is basically equivalent, slightly heavier than the proton, which is like if you combine, for our purposes, you can combine a proton and a electron, and that gives you the neutron. Okay, so again, this is more like a nuclear physics class. We haven't gotten to chemical reactions and whatnot. But these are the symbols and the masses and the things going on. And the mass of an electron is so small, we'll ignore it. But these symbols are, you need to know these for a proton, an electron, a neutron as we go on through the whole year. H plus is a hydrogen, but it's saying that there's just one proton, so they're equivalent. And it's understood that electrons are negative, so usually you have the sign there. It's understood that neutrons are neutral, so you usually don't have this little 0 there after this. Okay, why do we care? Is because every element has a unique number of protons. And so anything that has the same number of protons is that same element, and neither two are the same. We represent these, we're basically getting to the periodic table. We represent these with a capital letter and a lowercase. So a couple examples, at kids' birthday parties, you'll have balloons with helium in them. You can take and undo them and breathe it in, right? And it changes since the density of the helium is different, it changes the way your voice sounds. Kind of like if you scream underwater, that kind of thing. Then we call it pencil lead, but it's not really lead. It's really carbon that's in a pencil. And these are pure samples of different elements. And so we get to the modern periodic table. And I'll send everybody, post on Lalim and send out the periodic table I like the best. I just got it off Google Images a long time ago, but it's color coded and gives you a lot of information, so you don't have to go and look up individual elements or different periodic tables. It kind of has everything all in one. A good term to note, we'll see it again with nuclear chemistry, is isotope. And so an isotope is when you have an element that has a different number of neutrons. So it has the same number of protons because it's the same element, but it has a different number of neutrons. So for example, chlorine is the 17th element, and it's got two different isotopes. One that has a mass of 35 and a mass of 17. So it has to have the same number of protons because it's the same element, it's unique. But the mass is different because it has a different number of those neutrons. So the mass comes from the protons and the neutrons. These isotopes have different masses, which means a different number of neutrons. And they're showing you neon signs here because the way this works is they just put different mixtures of gases. And then when the little tubes of glass are evacuated, and then when you mix in different gases, it gives off different colors, which we'll get to in future chapters. Okay, so for neon, for example, neon has 10 protons, the 10th element. Then how many neutrons it has will determine the mass. So 10, 11, and 12 are the three that exist. So your mass then is 10 plus 10, 10 plus 11, or 10 plus 12, giving you a mass of 20, 21, or 22. But these show up in different abundances. So this is sort of like your grades in a class where, like for us, the midterm is worth 25% of the grade, but the final's worth 50% of the grade. So since 90.48% of the neon on Earth is this 20 isotope, then the mass of all neon when you mix it together needs to have what's called a weighted average. And the 20 isotope is more important. The 21 is nearly negligible, right? Just 0.27%. And then the 22 is the rest. So, around 90, almost, you could ignore it and 9%, or 90 and a half, and 9 and a quarter there. So then here's just a couple problems, and usually on a test, I have to make these up and use elements that aren't on the periodic table, or there'll be one that's on the periodic table. So for example, this one's saying how many protons, neutrons, and electrons are in this symbol, right? So 24 tells you what element, chromium. You go to the periodic table. There's no charge indicated, so that must mean that the protons and the electrons have the same number, and the mass comes from the protons and the neutrons. And the total was 52, the number up top. So you subtract 24 from 52, and there must be 28 neutrons for this particular isotope. So except for nuclear chemistry, when you have some chemical reactions, the elements don't change. So then what happens? The electrons move and they create different bonds, but still the protons and the neutrons don't change, and the element stays the same. It's just attached in a different way. Just some nomenclature so we're all on the same page. Ions means charge. The protons and electrons aren't the same. If you have more electrons, then it's negatively charged. That's called an anion. If you lose some electrons, then there's more protons, so it's positively charged, and that's called a cation. I think it goes into a bit of naming here, and this takes a little while. So we'll stop here. It's almost 1:45. We'll stop here at 47, slide 47, and pick up there. Monday is a holiday, so I know I kind of went fast through this chapter 1 and halfway through chapter 2, but part of that is because we don't have class on Monday, so I'll see you next week when we meet again, and we'll pick up here, and it looks like we're at 47. Yeah, it's about halfway through this chapter. Stop. And let me hit So, any questions, comments, thoughts, feelings? Okay, on La Lima, there's those worksheets, and they're labeled by week. So I know we went kind of fast, but we covered all of 1 in chapter 2. So it'd be a good idea. I mean, no need to rush off and do it now, but sometime before next Wednesday to at least do worksheet 1 and maybe worksheet 2 and see if you could get those problems on your own. If you've got other physics or engineering or bio classes, then you've probably had these topics overlap with one another and you have to do homework from others of those. Especially if you're taking chem and physics at the same time. But we're going to deviate here a little bit in chapter 3, and then chapter 4 is where we start doing actual chemistry, where you won't have overlap from any other class. Okay. It's been a while since I've had a class where I talk for an hour and 15 minutes straight, but now I need to go drink some water. Okay, hang around if you want, ask any questions or anything. I hit the unmute button, so you can unmute if you want, and if not, I'll see you next week. Yeah, you're welcome. Have a good weekend.